Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 18, Route Redistribution. And before we take a quick overview of what we're going to look at in this section, I want to give you a word of warning regarding route redistribution, especially as regards to production networks, because if we're working on it in our home lab or on rack rental, we can always take our time fixing it. That's how we learn, is to work with this stuff on real equipment. But with route redistribution, when you are looking at route redistribution in production networks, you're working with the IT equivalent of dynamite. And dynamite has good purposes, it has bad purposes. I'm not saying you should never redistribute routes, but I am going to tell you that proper planning is the #1 step in configuring successful route redistribution. We're going to see some specific examples in this video, but you'll also see that the ability to analyze the network design and possible points of conflict in advance are vital to performing proper route redistribution. It's not just about remembering some commands and then just typing them in one place, because in a production network, you just can't do it like that. So again, I want to mention one other thing before we get started here, that with route redistribution, for those of you with your eyes on the CCIE down the road, when you become a world-class route redistribution expert, and you can, then you're on your way to the CCIE. I think that's the #1 topic that trips people up. But I'll tell you, the only way to get good at it is a lot of practice. And I don't mean on simulators, I don't mean on software programs, I don't mean on anything pretending to be a router. I mean the real thing. Either your own home lab, renting some rack time, whatever you have to do. But that's just a word of advice from somebody who's been there and who has been exactly where you are right now. The only way to get good with route redistribution is to do it. And the only place you can practice it is on a home lab or a rack rental. So having said that, let's take a look at the overview. We're going to look at some automatic route redistribution scenarios first. And I'm going to tell you that most of these, unless you work with EIGRP, you may never see them. It's good stuff to know for the exam, though. And if you do work with EIGRP, these are important. We're going to talk about RIP and the seed metric. And the seed metric doesn't only go with RIP, but it'll be an important part of our lab, and we will discuss the seed metric in detail. We're going to look at two terms that you hear thrown around a lot: suboptimal routing and routing loops. And sometimes they get a little confused or used as they meant the same thing, and they don't. We'll take some looks at some illustrations of both of those. Preventing and fixing routing loops. There is no one-size-fits-all command for preventing routing loops. There is no such command as no RIP routing loop or no OSPF routing loop. Doesn't work that way. But as you're going to see, what we want to do is prevent them instead of fixing them. And analysis, the ability to analyze a network diagram, a network map, identify the possible problem areas before you do it, that is the key to success with route redistribution in the workplace. We're going to talk about administrative distance, but it's not going to be the same old CCNA administrative distance discussion. You know how that is. When you start the CCNA, it's almost the first thing somebody hands you is a list of administrative distances. You don't even know what some of the stuff is yet, but here are the administrative distances. We're going to talk about monitoring them and adjusting them. And we're going to do that on the rack and talk about how we verify that redistribution has taken place. We're going to do that throughout this video. And finally, we need to know how to filter redistributed routes. Because when we perform route redistribution, we may not want all the routes being exchanged between two protocols. So we need to know how to filter some of them out. And that's going to lead into a discussion of the null-zero interface, the dangers of BGP redistribution and things we have to look out for, and distribute less. So you probably hear more about watch out for this, or you don't want this to happen with route redistribution than with everything else total. And that's because if you misconfigure OSPF for a few minutes, or you're rolling it out and you misconfigure it at first, you can fix it without a lot of network interruption. But when you do route redistribution incorrectly, it can be really difficult to fix. And that's why you've got to get real hands-on work with it. Well, what the heck is route redistribution to begin with? Just a reminder here that it's the process of taking routes discovered by one method and placing them into another protocol's domain. And the reason I say method there is we get so caught up in watching the redistribution of dynamic routes that we forget sometimes to have true inter-protocol connectivity. We have to redistribute connected routes as well. That's the one everybody forgets. You can also redistribute static routes. We'll run iOS help here in a few minutes on the routers to see all the options. But don't get caught up in thinking, well, it's always one protocol to another, because it's not. Here are those automatic route redistribution scenarios I mentioned to you. There are 4 scenarios where routing protocols will automatically exchange routes. And I hate all 4 of them because it's not something that you want the protocols doing on their own. I have never seen automatic route redistribution in a production network that went well. Maybe you have, I have not. And the first one is the one you learned in the CCNA, is that IGRP and EIGRP will automatically exchange routes when they are both running the same AS number and, of course, running on the same router. The others are a little more esoteric regarding some EIGRP protocol-dependent modules, or PDMs. You learned about those in the EIGRP section. If you're running EIGRP for AppleTalk, that will automatically redistribute between 2 other protocols, plain old EIGRP and RTMP, which is the Routing Table Management Protocol. This is an AppleTalk routing protocol. And EIGRP for IPX, the Inter-Network Packet Exchange, it's a networking protocol used by Novell NetWare. That will automatically redistribute routes with IPX for RIP, or RIP for IPX, depending on how you want to look at it. Otherwise, it is SYN, ships in the night routing. And this is one of those phrases when you hear it, it's like, what does that mean? And if you never wanted to ask anybody what it meant, now you're going to know. It's ships in the night routing is simply what occurs when you have multiple routing protocols running on a single router and they're not exchanging routes. That's it. And this is a good example of ships in the night routing, and it's very typical of a network, is that we could have IGRP running on our local area network and OSPF running across our WAN. And we've got a core router here that would be running both. The OSPF domain is not going to know anything about the IGRP routes by default, and vice versa. And that's probably the way you want it. You would not want IGRP and OSPF automatically exchanging routes, because the problem is you're probably running private IP addressing in your local area network, and you can't advertise those out anyway. You don't want those leaking out onto the net. So this is ships in the night routing. Now we're going to get into RIP and the seed metric, and again, RIP and the seed metric is the most common redistribution error when it comes to the seed metric, but you've got to configure a seed metric for RIP, IGRP, and EIGRP anytime you redistribute routes into those 3 protocols. And it's required because of the difference between the metrics. Because let's think about that. If you were taking an OSPF route and redistributing it into RIP, which is actually what we're going to do in a few minutes, most of your OSPF metrics are going to be higher than 15. Basic OSPF route can have a cost of 65, a short path, I should say. And if you redistribute that into RIP, and RIP looks at that metric of 65, it doesn't have any idea what to do with it, so it's not going to accept it. It looks like it's unreachable to RIP. So what we're going to do is configure a seed metric at the time of redistribution, and what this serves at, it's a beginner metric. You're putting the route into RIP and saying, I'm going to give you a metric that you understand. And you could set it for 1 or 2, 3. It's not rocket science as far as what you set the seed metric to, it's just that you have to set one. And for IGRP and EIGRP, when we redistribute routes into those 2 protocols, we actually have to give a value for each of the 5 metric weights. Remember those? Bandwidth, delay, load, reliability, MTU. You got to set a value for all 5. So the redistribution command for those 2 looks kind of long. Now, you've heard me say a couple times in this course, and those of you who have taken other courses of mine or read my other books for other certifications, know that one thing I really love about Cisco routers and switches is that if you forget a value, it's going to tell you. You know, if you get to the end of an ACL, an extended ACL, and you know it's hanging off the screen, it's so long, and you forget to put a port number at the end, something like that, it's going to tell you. If you're about to do something you probably shouldn't do, it's going to tell you. It's going to give you a prompt saying, you sure you want to do that? And you know, if you see no for the prompt, you know you probably don't want to do that. This is not one of those situations, unfortunately, because the router will not remind you to configure the seed metric. The routes just won't be there. They will not be in the new domain. And that can really drive you crazy because you can do it. It looks correct. But when you look over in the domain that should have the new routes, they're not there. We are going to look at such a scenario like that in just a moment. I've set that up so you could see that in action. Now you may be thinking, well, you know, what about OSPF? What about IS to IS? Our link state protocols do not require seed metrics to be set. You can set them, but they have default seed metrics already. Really good values to know here at the bottom of the screen. OSPF will assign redistributed routes a default seed metric of 20. That can be changed. We actually changed it in the OSPF videos with the default cost command, but it has a default seed metric of 20. Always an exception. If you put BGP routes into OSPF, they're given a seed metric of 1. And then finally, IS to IS does officially give it a default seed metric, a redistributed route, but it's a seed metric of 0. So IS to IS, always a little different, as you know from watching the IS to IS videos. So let's go ahead and see this in action. It's great that we know the theory, but we want to see it in action. And this is what we're going to configure next. I have pre-configured the RIP and OSPF domains here. And we've got routers 1 and 2 in a RIP version 2 domain with auto summary turned off. And they are running over the 2110/24 network. Routers 1 and 3 are in an OSPF domain. It's OSPF area 0. It's the only area we have over there. Over the 172.16.13.0/24 network. Now, router 3 is also connected to an Ethernet segment, 172.12.34.0/24. And what you see in the arrow going from OSPF to RIP is what we want to have happen. We want router 2 to see that route to 172.12.34.0. We put a metric or 2 in there, but we'll assign whatever metric we want to because it's our network. But first, let's bring that pod up and let's bring our rack up. And a couple of things I'm going to tell you here initially. You may roll your eyes a little bit and say, well, you know, of course I would do that anyway. Trust me, some of these initial steps get missed sometimes, and it leads to a real headache. Sometimes we're so busy concerning ourselves about the complex part of a configuration, we forget about the basic part of it. Happens to everybody. Let's take a look first at router 1. That's our border router right now between RIP and OSPF. And we're going to run show IP protocols. And we see that it is running OSPF 1. It's running over the 172.16.13.0 network, and that's the one between router 1 and router 3 that we expect to see. And it's also running RIP over the network 20.0.0.0. And please note that we have configured it for version 2. You know how we did that with the version 2 command. It is sending and receiving version 2 only, and that automatic network summarization is not in effect. So let's take a look at our RIP routing table right now, and we don't have anything on OSPF, on RIP. Let's see what we have in OSPF. RIP does have one route, and that is the Ethernet segment connected to router 3. You can see the administrative distance here is 110, as we expect, in the brackets, and the second number is the cost in OSPF. That's our OSPF metric. So if we redistribute a route into RIP that has a metric of 74, RIP's just not going to accept that. But we'll try anyway. On router 2, we'll run show IP protocols. You can see that it is running RIP version 2. Auto summary has been turned off, and we'll do a quick check of the routing table over here, and we don't see anything. Router 3 finally always runs show IP protocols before you do something like this, and it is running OSPF. It's running over the direct connection to router 1, which is 16.13.0, and it is advertising 172.12.34.0. So what we're going to do then, let's go back up to router 1. Again, we're going to take this route that's in OSPF and place it into the RIP domain. And we're going to use the redistribute command to do that. Under the RIP domain, redistribute, and remember I told you a few minutes ago that we have to keep in mind that not only can we redistribute dynamically discovered routes, which is what most of these are. Some of these you see are new friends of yours from this course, ODR, that kind of thing. We can also redistribute connected routes, and we can redistribute static routes. But right now what we're going to do is redistribute all OSPF routes, and we only have one. So there we go. We just did a redistribute OSPF 1, 1 being the process number. We'll do a WR at the same time. And we will go over to router 2. Since we're running RIP over here, we'll run clear IP route asterisk to go ahead and hurry it up because we're impatient. And we don't have any routes yet. And we don't have that route yet. We're not seeing the route. Still don't see it. Probably would have seen it by this time, don't you think? So what we're going to do, what we always do in this kind of situation, if we're not seeing a route that we expect to see, we start running debugs because we know how things work and we want to see what's going on with the updates that are coming in from router 1. And the RIP debug is very simple. Debug IP RIP, and we're going to clear the routing table again so we can hurry up and see what's going on here. And we see some request. Of course, the request is going out to 224.0.0.9. And we got a version 2 update, but all I'm seeing here is the connected route to begin with, 2110/24. So I don't see anything in here about getting a packet from router 1 that contains that OSPF route. The problem is that we did not set a default metric or a seed metric for that route. So that's what happens, and you could see, let's go back up to the configuration we put on 1. When we put in redistribute OSPF, I mean, that looks right. Right there at the bottom of the router screen, that looks right. And that's what all the books say to do, redistribute OSPF 1. And you hit enter and the router didn't tell you, hey, you got to put a seed metric in. You have to know you've got to put a seed metric in. You also have to be careful in the real world and in the home labs when you are removing and adding redistribute commands. Because sometimes if you have a long redistribute command and you put, no and then repeat the command to take it off, it may not come all the way off. It may actually retain the basic redistribute command. I kid you not. We're going to test that here and see if we see that here today. So what I always do is remove the previous redistribute command. Don't just type redistribute OSPF 1 and then something else. So let's go back out to redistribute OSPF 1, that command. There's the command we were going to use. Now let's use iOS help. And you always, I don't care, when you're a quadruple CCIE, you should still be using iOS help to see these details. It's so informative and so many people just ignore it. And we see something called match here for redistribution of OSPF routes. That's not really what we want right here, though. That's more advanced stuff. Route map reference, VRF, couldn't care less. We see a CR there, in the arrowheads, which means that this is a command that we could just hit enter right now and it would take it. That's what we did before, but it didn't work. Well, what we're going to do is set the seed metric for redistributed routes. And you can see now that the default metric, the seed metric that we're setting, has a value of 0 through 16. We obviously don't want to set it to 16 or bad things are going to happen since this is RIP. We're going to give it a seed metric of 2, just like we saw in the diagram. So now we have redistributed the OSPF routes into RIP with a metric of 2. And like I said, I like to take that original redistribute command off. So while we're doing that right on router 1, let's go down to router 2 and see if we see these routes yet. Hey, look at that. Now we see them. And we see both routes that are OSPF enabled on router 1. Remember, router 1 only had one OSPF route in its table, but it's running OSPF on that other one. So RIP is actually going to advertise 2 routes to router 2. The directly connected interface or network between 1 and 3, it's going to get that, and it's going to get that. And that's what we wanted. So you see firsthand that the metric, the seed metric, is what we needed to run to get redistribution to work with RIP. And the same is true for IGRP and for EIGRP. So now that router 2's got these 2 routes, we should be able to ping those interfaces, say 172.12.34.3, which is router 3's Ethernet interface. So let's give that a try. Doesn't look good. Doesn't look good. So we've got the route to 172.12.34.0. That's not a problem. So why can't we ping? We see the routes, but the pings didn't go through. Now we're going to draw back on our CCNA knowledge base here and start using it to become expert level network troubleshooters. Pings only show us that there is an IP connectivity issue. And I don't have to be a genius to look at that and say, hey, we don't have connectivity. Pings show us that there is a problem, but it doesn't show us where the problem might be. And what we do for that is trace route. So we're going to do a trace route on 172.12.34.3. And you could see where this would be confusing for some people as far as the pings not going through. And it may be confusing for you. It was for me the first time I saw this kind of configuration because you're thinking, well, it's got the routes. What's the problem? Well, we got to be able to find where the problem is. And trace route's doing a pretty good job of showing us immediately where the problem is. It seems to be on router 1 because then we're just getting timeouts after the packets get to 2111. And this is where knowing that escape sequence really comes in handy because you know how many rows we get for this? 30. And it's really bad when somebody's looking over your shoulder and you have to sit there and pretend like, yeah, I'm expecting this. Again, it's Control-Shift-6, Control-Shift-6. And you could see on the router immediately that the trace route was aborted. I have never understood why they don't say what the escape sequence is there. It's one of the highest searched Google Cisco terms, period, is what is escape sequence. So now you know what it is. You don't have to Google for it. So let's go up to router 1. And see if we can ping 172.12.34.3. Yeah, no problem. We expected to be able to. That's in the OSPF domain. So this is interesting. Now let's take a look at the network diagram here. So router 2 is trying to ping that Ethernet segment. We successfully configured route redistribution. We looked at router 2's routing table. Everything looked good. But RIP, the RIP router, R2 can't send pings over, but R1 can send them with no problem. The real problem here is that the OSPF domain doesn't have a path to get back to router 2. It doesn't have any idea how to get there. So the pings cannot possibly get back. We've got to remember that. We concentrate sometimes with pings about can the pings get to the remote destination. Sometimes they can get there, but they can't always get back. So we've got a couple of options here. We could put a static route on router 3 to give it a path back to R2, or we could perform two-way route redistribution, which is what we're going to do here, because there's a message with OSPF redistribution that you need to be aware of. So we're on router 1. Now we're going to go under the OSPF domain and configure redistribution. Now, you recall a few minutes ago I mentioned that our link state protocols, OSPF and ISDIS, do not require a seed metric. So when I hit enter here for redistribute RIP, I should be fine. Let's see what happens. I get a little message that says only classful networks will be redistributed. So right now we have redistribution working, but the only networks that will be redistributed will be classful network numbers. And I think it's safe to say that the one we're trying to get over there, this segment, 2110, that's not classful. But let's test that and go down to router 3 and see if router 3 sees this route. And it does not. Remember, router 3 is not going to show any routes as OSPF right now because the two OSPF enabled routes are directly connected. That's good to keep in mind for an exam question too. So, we got to do something up here on router 1. And the first thing we're going to do is get rid of the previous command. I'm going to take that redistribute RIP off. And let's take a look at our options here with iOS help. And you see the metric type, which you recall with OSPF, we've got E1 and E2 different kinds of routes when they're redistributed. Subnets is what we're looking for here. We don't have to set a seed metric, but if we want subnets to be redistributed in OSPF, we have to add this word to the end of the command. So we're going to do that. And that should be enough, but officially it's subnets. We will do a save there, go down to 3. And there it is. Just that simple. That time the router gave us a little warning. Hey, what you just put in is okay, but you're only going to see classful network numbers. That word subnets gets left off a lot. Good exam question, good real world stuff to know. And you know from our earlier discussion in OSPF that this is shown as an E2 route by default. That's the OSPF redistributed route default. And that means that the cost shown here in the brackets reflects only the cost of the path from the ASBR, which is router 1, to the destination network. And you can see that that just happens to be 20, which is our default seed metric. Good stuff to know. Let's see if routers 3 and 2 can now communicate. And we'll do a ping on 3 first to 20.1.1.2. Goes through just fine. We go over to 2 and ping the previously unreachable 172.12.34.3. Goes right through. We have no problems. Now this is about as simple as route redistribution is ever going to get in life. Okay, this is as simple as it's going to get. We really have no place where a routing loop can occur. We have only one router connecting the two routing protocols. So route loops, routing feedback, we really can't get any of that stuff. This is as safe as it gets, and you can see that even this got pretty involved. We had to remember to put a seed metric on the RIP route, on the OSPF route that was being put in a RIP. We had to remember to put the subnets option on the end of redistribute RIP before we could finally have connectivity. And again, you could see where just looking at routing tables is not enough. And that's one of the lessons you really learn when you're becoming a CCNP. Just looking in routing tables is not effective troubleshooting, because you could see on router 2's routing table that, well, this ping should go through. It's got a route to that destination. Yeah, but the destination didn't know how to get back. It couldn't get back. So it was just stopping at router 1. So that's as simple as it gets. It gets a little involved, and that's why we're going to spend some serious time here on redistribution theory, as well as looking at some more hands-on examples. We have plenty of that to come too. Let's take a look at suboptimal routing and routing loops and discuss those for just a few minutes. The difference between the two is that with suboptimal routing, the data is going to get to the destination, but it takes the long way in getting there. It does not take the most effective path. And routing loops, that means that the data is going to go around in a circle, a logical loop, at some point in the network and can't get to the destination. So suboptimal routing means the data is getting there, just not as fast as we would like. But the routing loop, it's never going to get there. And trace routes are excellent routing loop detectors. Pings are not going to show that. Pings are just going to finally time out or give you some really strange feedback. But a trace route, what to look out for there is seeing the same 2 or 3 or 4 IP addresses continually showing up in your trace route. You'll be able to spot it very quickly with a trace route because it's going to end pretty quickly. But the thing is, when you look at the route, it's going to be the same couple of IP addresses in the trace route. And that means that those 2 or 3 or 4 IP addresses, those devices are just sending the data back and forth between each other. It usually takes 3 devices. That's why we call it a loop. So let's take a look at a suboptimal routing scenario. Suboptimal routing generally occurs because of a miscalculation in coming up with a seed metric value. So we have to kind of be careful about that because the packets will eventually get to where they're supposed to go, but the key word there is eventually. Suboptimal routing, it's routing that works, but not as well as it should. And here, router 2 has 2 possible paths to send data to 172.12.34.0. It could go through the path router 1, router 4, router 3, or it could just go to router 1 and then be sent to router 3. Now, all other values being equal with RIP, the best path is going to be the more direct path because RIP only understands hop count. But if we perform route redistribution in here and we set the wrong metrics, R2 could end up using the longer path. And it would go from router 2 to router 1 to router 4 to router 3. Data would still get to where it's going, but it would put an unnecessary strain, first off, on router 4's resources, because router 4 shouldn't even be involved in that. It's great to have redundancy, but we would want the data going from router 2 to that Ethernet segment to just go to router 1 and then to router 3. That's not the end of the world, but a routing loop can be. And in this drawing, we see that the packets have actually entered a routing loop. And they're going to go back and forth between the same group of routers over and over and over. And again, traceroute is an excellent tool to detect a routing loop. That's why you don't want to just rely on pings. Through some kind of misconfigured route redistribution here, router 3 has gotten the idea that to send data to 172.12.34.0, it should send it to R2. And then R2 sends it to R1. And then R1 sends it to R3. And now we're in a routing loop. That data cannot possibly get to 172.12.34.0. That's a routing loop. And again, when we talk about preventing routing loops and then fixing them, there is no one-size-fits-all solution for routing loops. Because the solution that you use is going to depend on your network topology. It's going to depend on where the routing loop could take place. It's going to depend on the pre-existing configuration. This is where your analytical skills are really going to come home for you. They're really going to help you get the job done. Now, having said that, we're going to look at some routing loop prevention mechanisms that Cisco is going to expect you to know to pass this exam, but also that you should know about each one of these in order to formulate the proper strategy for your particular network. Now, the first solution is having a sound network design in the first place, which is why it's more than worth your time to take the time to analyze your network topology. I know sometimes your client's in a hurry. I know sometimes your company may be leaning on you, but route redistribution is not something you can do quickly. You don't just sit down and bang it out and see what happens. Now, if you're lucky, you'll see a network a lot like this one. Because in this network, we have one point where redistribution could possibly take place. The only interconnection between these two domains is at the point of redistribution itself. Now, this network setup would cut your chances of routing loops greatly. Again, because the only interconnectivity between the RIP and OSPF domains is at the point of route redistribution. Because one of the things you've got to decide in advance is where your protocol border routers are. That's where both protocols involved in redistribution are configured. You are not going to see networks designed like this terribly often, because what many networks have are multiple connectivity points, and we want that generally. We want that for redundancy's sake. And we love redundancy in this business, and you're going to think it's a great idea until you're looking at something like this. Then you're going to hate it when it comes to route redistribution. This is great for network fault tolerance and a living nightmare waiting to happen for route redistribution. Because we actually have 4 different points where these two protocols could possibly interact. And while router 1 is still the best location for redistribution to be configured, what you'd have to concern yourself with here are routes being sent back and forth between the other routers. Because routers 2 and 3 are connected, routers 5 and 4 have a logical connection, 1 and 2 and 1 and 3. We've got 4 different places where routers in one protocol could possibly talk to another. Now, I've worked personally with the last configuration we looked at and then one like this, and this is much more common. The most important part of route redistribution is planning it, and the first part of that plan is identifying your boundary routers. Write that down. You've got to identify every boundary router, and it's not always obvious when you go to a client site, because let's face it, their network maps aren't always the best. Sometimes they're fantastic. Sometimes they're not. You need to look out there for yourself a bit and do that in advance. What Cisco recommends in situations with multiple boundary routers that you should do is use one-way route redistribution. Cisco says that, and I'm with them. Anytime you can use one-way route redistribution to make things happen, that's what you should do. And now we're going to take a look at how changing some administrative distances or fine-tuning some can help us avoid suboptimal routing and routing loops during a route redistribution scenario. And what we're going to use in this particular lab is this network. Routers 1, 2, and 3 are running over the 172.12.123.0 network using their router numbers as the last octet, and they are running RIP. Router 1 is also advertising an Ethernet segment 10.110/24 into the RIP domain. We also have an OSPF domain where routers 2, 3, 4, and 5 are in area 0 via their Ethernet interfaces on the network 30.110/24. Again, planning is the most important part of route redistribution. And we've decided in advance here to make router 3 the ASBR, the router that actually performs the redistribution of the RIP routes into OSPF. But we have 2 boundary routers here, and you want to make sure not to get these terms confused. ASBR is an OSPF only term. But a boundary router is simply a router like 2 and 3 here that are running multiple protocols. They're bordering the protocol domains. And what you must watch out for is not only getting the configuration right on 3 here, but making sure that your other boundary routers do not fall victim to suboptimal routing, because that happens very often. We don't really have a chance for a routing loop here because we're going to follow Cisco's recommendation and perform route redistribution only on one of the boundary routers, and that's going to be R3. But it's my experience in the field and in the classroom that we're so intent on getting the redistribution right on 3 that we ignore what may happen on other boundary routers. So I think that's enough of a hint as to what might happen here in this lab. This is an excellent time for you to jot this down, this entire network. You may want to go ahead and pause the video and print the screen because we are going to be tracing some routes throughout the redistribution process. And speaking of that redistribution process and administrative distance period, just a quick review. You recall certainly that AD is only used when there is no longest match in the routing table. We're looking for the longest prefix, and if we have a tie and the prefix length for a destination network is the same but on two different routes but 2 different protocols are reporting them, there's got to be a tiebreaker, and that tiebreaker is the administrative distance. As far as verifying redistribution, you want to verify before and after. On your boundary router, the one that's actually going to perform the redistribution, you always want to run show IP route to take a look at the routes that you're going to redistribute. Because here we've only got one. We're kind of tracing that one as it travels through the network. But you may have 50, you may have 100, and you may not want all those routes to be redistributed. We're going to show you how to filter those later in this video. But for right now, we're going to run show IP route on 3 to make sure it has the route. And afterwards, you want to run show IP protocols on your border router and show IP route on the other routers just to make sure everything looks good. You also want to make sure that your other boundary routers are not suffering from suboptimal routing. So it's actually a good idea for us to go to both of our boundary routers right now, 2 and 3, and just see what their route to that Ethernet segment looks like in RIP. So we're going to go down to router 2 here, and we're going to show IP route RIP. And we see the route. Everything looks fine. The next hop is 123.1. Those next hops are what you want to watch. So everything looks fine there. I'm going to go to router 3, which is actually going to act as our ASBR. And everything looks fine there. The next hop is 123.1. The route is there. And we're ready to go. But it's a good idea to note the next hop IP addresses for the routes being redistributed on all of your boundary routers, not just your ASBR. So we on router 3 are going to perform two-way route redistribution. What we're going to do is redistribute the RIP routes or route into OSPF. We're also going to go ahead and redistribute the connected routes into both protocols, just to make sure we don't have an intermediate IP connectivity issue. It never hurts to go ahead and redistribute your connected routes. So under OSPF 1, what do we need to do for RIP here? We need to do something else here. It's a seed metric or subnets. We're redistributing a protocol into OSPF, so we do not need to set a seed metric. It's got a seed metric default of 20. But we do have to have the subnets keyword on here if we want the subnets to be advertised into OSPF. We're going to do the same for the connected interfaces, the connected routes. So everything looks good there. Under RIP, we're going to redistribute the connected subnets in to RIP. We don't type subnets here, though. What do we need? We need a seed metric. And we'll set a metric of 1 for the connected routes. We'll also spell redistribute correctly. So we're all set. Watch those redistribute connected routes, because they can interfere with your IP connectivity. And as you saw in a previous video, they're kind of hard to spot. So let's go down to router 4. We're going to look at 4, 5, and 2. It looks like redistribution went fine. We didn't see any issues. And if we run show IP protocols on router 3, you can see a couple of different things right off the bat. First off, router 3 is now an ASBR because it's performing redistribution into OSPF, and it's redistributing connected routes and RIP routes and includes subnets in both. If you do not see this, that means you're only getting the classful network numbers. That's why we're double checking it. And with RIP, pretty much the same information. You're not going to see a whole lot of redistribution information here. You'll just see the redistribution connected in RIP because we are not putting the OSPF routes into RIP, but we are putting the connected ones. So let's start taking a look around our table, or around our network then. And we're going to go to 4, and then 5, and then 2. And just see what we see. And we're just going to look at the OSPF routes. There's no use to look at the full table. We see 2 routes. We see 172.12.123.0, which is the frame network, and we see the remote Ethernet segment being redistributed. This is what we want. That's why we went ahead and did connected while we were at it. Now, you recall from your OSPF studies that E2 is the default metric for routes learned via redistribution, and it includes the cost only from the ASBR to that network. And you can see that nothing much changed along the meantime because there's our default seed metric of 20. So when we look at that cost, and that's the OSPF metric cost, it's not reflecting the path of the entire cost from 4 to 3 to 1. It's just reflecting the cost from the ASBR to the destination networks. That is the default for OSPF. Everything looks pretty good so far. We see next hop IP addresses of 3113, which is what we expect. That's router 3's Ethernet. So now let's go over to R5. I have a feeling it's going to look much the same. And it does. We see both routes. We see they're both E2 routes. That's our default. We see the seed metric of 20. And we see that the next hop is 3113. But now we're going to go up to router 2. And we're going to take a look at which table first. Let's take a look at its OSPF table. Okay, there's the redistributed route. And we see it's an E2. We see the next hop is 3113. What about RIP, though? Because if you recall, it was learning about it via RIP in the first place, remember? That's how we set it up. Router 1 is advertising that network to router 2, and so what's the problem? Is there a RIP route? Will there be one? No, there won't be. Because you recall, when we looked at R2's next hop for that IP address to begin with, it was router 1. When router 2 was originally sending packets to this network, it was going straight to router 1 and then delivered from there. Now, though, the next hop is showing as router 3, which means that it's going through the Ethernet to router 3, up to router 1, and then finally to the network. That is suboptimal routing. We don't expect, and let's bring the tables back up here, looking at the OSPF and RIP tables. We don't expect 172.12.123.0 to show up in the RIP or OSPF routing tables because it's a directly connected network. But the route to 10.1.1.0 is now using R3's Ethernet interface as a next hop IP address, and it's now an OSPF route. Now, even though OSPF is thought of as a better protocol than RIP, any data sent to R2 right now to the network 10.1.1.0 is going to take a longer path. It's going to go from 2 to 3 up to 1 through the cloud and then out to the Ethernet. That's suboptimal routing, because with the RIP path, it was going straight to R1. Now, why did router 2 choose the longest path? That's the kind of thing we have to be ready to analyze as network engineers. Now, of course, if you think about the name of this particular section of the lecture, you probably have a pretty good idea. Here's our network in action right now. And the problem is that router 2 right now is getting 2 routes for the network 10110. And we want that. That's redundancy. We like that. The issue, though, is that one of the updates is coming directly from router 1 via RIP. And the other is going over the Ethernet, which is why I put 2 arrows on that double-headed arrow there. Because it's on Ethernet and everybody on that segment's going to see it. Well, the prefix length of 24 is the same for both updates. So now we go to administrative distance as a tiebreaker, and that's where the issue comes in. Because OSPF has an AD of 110, RIP's got one of 120, so the OSPF route is chosen even though we can see it's not the best route. Now, you would have noticed this by looking at the table, and this is another reason why I like using show IP route OSPF and RIP instead of, just show IP route. Because you might not have noticed it then, because, you see the route still in the table, you don't pay any attention to it, you're just glad you've got connectivity, and certainly the pings are still going to go through. No problem there. But that just shows us that we've got connectivity. It's a good idea to check all the routes on any border router not performing redistribution with traceroute, because it's going to show you what the path is. So let's do that. Traceroute 10111. And you can see that the next hop IP address for traceroute, when it's going through, is 3113. You could also see that in the routing table. But for a larger network, traceroute will show you the exact path it's taking that you may not be able to figure out just by looking at a routing table. So right now, even though we have IP connectivity, this is a good example of suboptimal routing. We have 3 real options here. We can fine-tune the administrative distance. We could actually change the route's metrics, or we could filter the routes with distribute lists. We could filter that OSPF route. That's going to be covered in a later section. But personally, I've always found the best approach is to change the AD of the protocol on a router. We don't really want to filter any routes here because, again, looking at our network diagram, we have redundancy. If something happens to the frame network between 1 and 2, we want data to still be able to get from router 2 to that Ethernet segment. And here it could. If something goes wrong with the Ethernet segment, then router 2 could use the frame. So we don't want to filter any routes here. We like that redundancy. I'll take all the redundancy I can get. But what we're going to do here is actually change the administrative distance of OSPF on router 2. That's the one we're going to check. We're going to select. And this is how to change the AD of a protocol on a router. Very simple, but you got to know the command. We actually do this with the distance command. And I'll use iOS help to show you. We can set an administrative distance or an OSPF distance. That OSPF distance will come to you during your more advanced routing studies, your CCIE studies. But what we're going to do is change the administrative distance on this router only for OSPF to 200. So we just did it. We don't lose adjacencies, anything like that. Let's take a look at our OSPF table. Just that fast, we don't see the route anymore. We will see it, though, with RIP, because now we have corrected the problem and we're using the more direct route. It's just that fast, especially with OSPF. You know how fast OSPF works. So now when we run a trace route to 10.1.1.1, you can see it's going immediately to 172.12.123.1. That's how you change the administrative distance of a protocol on a router basis, a global basis, if you will. Because now every OSPF route that router 2 has is going to have an AD of 200. So you got to be careful with that one. And again, you'll learn later, and you can certainly dig into this on your own, you can change the distance of a route instead of the entire protocol. But we still have redundancy. And what we're going to do is prove that by bringing the link down from router 2 to router 1. We're going to disable that serial interface. And we should see several fun messages here when we do this. There goes the line protocol. Everything is going down. Let's take a look at our routing tables right now. The RIP route's already gone. And now, just that quickly, the OSPF routes are back in the routing table on 2. We have our redundancy, and you can see that the administrative distance is indeed changed to 200. So pretty cool stuff. Again, you have to be really careful using an all or nothing command when it comes to your routing table, and that's just what the distance command does. And it's going to change the AD of all the routes acquired from a given protocol. And again, you can certainly dig into this on your own. I think that's a great idea. You can go out to that Cisco website I gave you, /UniverseCD, and look it up about how to change the AD of a specific route or group of routes, but that is way outside the BSCI scope. Now, before we go on to another example, let's go over to router 3. And there's always a chance that you may want to send a default route from the ASBR when you're configuring redistribution. Now, you know that default routes are generated when we have stub and total stub areas. You've seen those, and you've configured those. But you also know that we can't make area 0 a stub or total stub area, and that's the only area we have right now. What we can do, though, is run an OSPF command called default information originate, and it's got an always option. And what this will do is send a default route to all the other OSPF routers. And when we put the always keyword in the end, that allows the router to propagate a default route without actually having one. Because without that, the router would have to have a default route in its table in order to advertise one. So that sounds kind of long-winded in theory, but let's take a look at how easy it is. Under the OSPF process, we are going to look at the default information originate command. That's quite a mouthful. And we do have a hyphen there in a strange place. Originate. And let's look at our options here. And what we're going to do is put in the always option. That way router 3 doesn't actually have to have a default route to propagate it. It's basically saying to the other routers, I'm your default gateway. So let's see that in action. Let's type always. And now the other OSPF routers will have a default route in their table pointing to who? Who are they going to point to? They're going to point to 30113 as the default gateway. And you can see here again we've got a default route, and notice that's marked as E2 because it's really considered a connected route on router 3. It's an E2 route with an asterisk next to it indicating a candidate default. And if we use the full command show IP route, you will see that with that command we set the gateway of last resort to router 3's Ethernet interface, and it's to network 0000. Keep in mind, very important difference here between default information originate and default information originate always. If router 3 in this scenario already had a default route, we could just put default information originate, and that will propagate the static route into the OSPF domain. But since router 3 didn't have one, and we are really just wanting router 3 to serve as the default gateway for all the other routers here for OSPF, we had to put the always option on the end of that command. Very important detail, and I wouldn't be surprised to see that pop up on your exam as well.